This video is intended to be a brief overview of the process of creating a database for the purpose of answering a research question of interest to you. I'm assuming that you already have a question that's important to you and have prepared an outline of the statistical analysis. Your database will need to be of a size and structure to feed into that analysis. For example, your question might be whether functional status at diagnosis helps predict survival among patients newly diagnosed with metastatic non-small cell lung cancer. If so, then among others, this information could be used to fine-tune a predictive model of survival, and thus help you better counsel your patients. This is an example of a simple statistical analysis plan. It's okay if you're unfamiliar with the techniques of survival analysis. Your statistician can help. For the purposes of communicating your intentions, it's sufficient to draw the survival curves in the next slide, and to say that you'd also like to create an equivalent set of curves after controlling for various other predictors of survival. In fact, asking whether functional status matters after controlling for various other predictors of survival serves to fine-tune your research question. Since functional status will really only matter if its contribution is unique and adds something to the impact of those predictors that are already available to you. Drawing this picture is all that you really need to do. Functional status might actually be recorded using a continuous variable, for example, a Karnofsky score. To make the figure simple, I've combined patients with similar Karnofsky scores into groups. The database will be rectangular with one row per patient. The columns include identifiers such as a unit number, 2 columns for the outcome. Turns out that follow-up time and a censoring indicator are both needed in order to accomplish a survival analysis. The primary predictor, which represents functional status, and then the other predictors of mortality, which statisticians term covariates. As a researcher, I'll have various questions, for example, as listed on this slide, pertaining to the quality and the appropriateness of the dataset. Just to highlight some of these questions, I'll need to clarify the inclusion and exclusion criteria for the study. For example, in assuming that my source is an administrative database, I might want to be assured that I can successfully identify patients near the time that the patient's cancer is advanced to stage 4. More generally, my inclusion and exclusion criteria will involve a trade-off between the desire to have a more homogeneous group, which would be smaller, although it would result in cleaner inference, and a less homogeneous group, which would be larger, but might result in an analysis that's less clean. I'll also be critically concerned with data quality as broadly defined. For example, do I have good instruments? Are the data present, that is, non-missing, and accurate? How many patients drop out of the data set? Is there a pattern to this dropout that will undermine my conclusions? Finally, I'll want to be reassured that my database is large enough to answer my research question. This slide illustrates the logic of a sample size calculation. There are better ways to perform the calculation in this example. My point here is to illustrate the sort of inputs that your statistician will ask you to supply. Before you go any farther, it's good to make a formal decision that the data set is of sufficient size, quality, and composition to proceed. There's a lot to be said for listing the strengths and weaknesses of the data set and showing the list to your colleagues and asking them whether the data set's good enough. If you plan to write a manuscript or other report at the end of the day, the list can become the basis of the limitations section of that document. Continuing to assume for simplicity that you'll be pulling data from an administrative database and intentionally oversimplifying things a bit, can be helpful to know that your database can be thought of as having 3 structures. The actual structure might be something other than a flat file. In fact, a very large database might not even be stored in its entirety. Instead, what's actually stored are the bits and pieces of the database, plus directions about how to assemble those bits and pieces if needed. Even if the data set is small enough to physically store, it might not be stored in the same structure that you'll ultimately use to analyze your data. For example, suppose you've conceptualized your analysis file to have 1 row per patient with 999 columns consisting of a record of whether each of the 999 drugs was provided to the patient. This is a large file. For each patient, you'd have 1 row and 1,000 columns. That is, 1 for each of the 999 drugs, plus a patient identifier. Instead, the data will probably actually be stored as having one row per patient per drug. You now have a much smaller file with 6 rows and 3 columns. That is, 1 column for patient identifier, 1 for the drug number within patient, 1 for the drug name. In any event, no matter how the data is stored, in almost every case, what you want to do is request that someone download a flat file for you. That someone might be you, assuming you've become sufficiently facile with querying data, with creating queries using deduce. If, instead of an existing database, you'll be collecting your own data, then you can structure the original data collection to be in a form that's convenient to you. Some recommendations about requesting downloads from others. First, minimize the amount of processing that you ask others to do. Ideally, just have them create a simple flat file and leave it at that. Within reason, ask for everything you want. You can always delete patients and or variables without having to ask someone to download the data again. Do as much troubleshooting as you can ahead of time. Also, check the data set for consistency as soon as you can. If you have to ask someone to download another copy, it's more humane to do so right away, while that person has his or her programs in hand. The next few slides illustrate the building blocks of the sort of restructuring you can easily learn how to do, or have someone do for you. This slide illustrates how to transpose a data set. This slide illustrates taking a subset, in this case of the males. This slide illustrates stacking 2 data sets. This operation can be problematic if the variables in question don't match. This slide illustrates aggregation. In this case, all of the values for a particular patient are summed. Here's one type of restructuring. A file with 1 record per patient per time point is restructured to have 1 record per patient. And here's the same process in reverse. This slide illustrates one-to-one merging. If everyone is present in both data sets, the output will have the same number of rows as the originals. This slide illustrates many-to-one merging. For example, gender is appended to each row of each patient's data. Merging becomes complicated when the identifying variables don't match. It's a slide on something that can save your career. Please manage your data reproducibly. At its heart, all you really need to do is save your original raw data, save the changes that you make, plus the rationale for those changes, and save the programs you use to analyze your data. The result will be auditable. Your statistician can help you set up a system to do so. This slide makes a distinction between the changes that you'll permanently make to the data, for example by changing a temperature value from 986 to 98.6, with those you temporarily make for the duration of a data analysis. Is cutting and pasting within an Excel spreadsheet reproducible? No, not at all. At least not as this operation is typically practiced. Excel can be made to work reproducibly, but what you'll need to do is save both the original raw data and the cleaned analysis file. You also need to document the reasons for changes, for example, either using annotated computer code that sets all systolic blood pressure values above a certain level to missing, or makes the changes 1 data element at a time. In summary, the database has rows and columns. The rows represent the natural unit of aggregation, which will depend on context. The columns represent the data being collected. Identifying variables are treated differently from the rest. A data set is more than just a rectangular array of information. It also contains meta-documentation, for example, about its history, its variable names, the codes for what the data values represent, and much more. Okay, let's practice. Your study question pertains to whether members of certain classes of drugs can be dropped for patients with life-limiting medical conditions. You're considering using an administrative database to help provide a preliminary answer. This final set of slides contains some questions that you'll need to answer before proceeding. We'll consider these questions as a group. So how would you fine-tune the data analysis? What statistical analyses would you perform? How would the desired database be structured? And how would you decide whether that database is good enough for you to proceed?